So welcome to everyone to this new meeting for the under 40 lecture series on combustion. It is our pleasure today to have Professor Stathis Tingas. Let me briefly introduce our speaker and his talk. So he's a chartered engineer and also a fellow of the higher education of the Higher Education Academy. He has earned his PhD in mechanics from the National University of Athens in Greece in 2016. Then he has been working for over 10 years in the Greek Air Force as a military jet engine engineer before relocating to KAUST as a postdoctoral fellow in the group of Professor Ongim. In 2019, he moved to the UK, and they actually got a position as a lecturer at the Edinburgh Napier University. And this research includes combustion, beyond combustion, also computational biology, mathematical epidemiology, and in combustion, his interests are related to numerical simulation, high-fidelity numerical simulation, combustion engine modeling and simulation, and also asymptotic analysis of combustion phenomena, as well as model reduction. Stathis, it's really a pleasure to have you here for our lecture series. And I'm really looking forward to your presentation that will target transforming zero carbon engines. And so you will give insight on the use of hydrogen peroxide in hydrogen ammonia combustion. Thanks again, and I give you the floor.
Okay, thank you very much, Alessandro, for the kind introduction and the opportunity to present my work in this seminar. Hello, everyone. Thank you for taking the time to be here. I'm very excited to present you some of my most recent work on the use of hydrogen peroxide in hydrogen and ammonia combustion. Before we move further, let me first acknowledge the support from my current collaborators at Imperial College and KAUST, as well as my past collaborators in the University of Glasgow, Brunel University of London, and my former students, of course. The plan for today is that I will firstly talk about the motivation of this work, and then I will move on to the main body, which is split into 3 sections. So fundamentals, theoretical engine model work, and the comprehensive engine model work. So as already mentioned in the title, the current project focuses on heavy-duty applications like ships and trucks, for instance. The decarbonization of these applications through electrification has not been very attractive so far, particularly for long-haul modes of transport. There are many reasons for that. I'm not going to discuss them here, but there seems to be a consensus both among policymakers and the research community that there is no clear solution to their decarbonization. Yet, several nations and international organizations have already set clear goals aiming at their decarbonization. For example, the IMO has established increasingly strict regulations on emissions with the ultimate goal of reducing emissions. At the same time, hydrogen and ammonia, which is considered a hydrogen vector, have been identified as key players in the decarbonization of our society, not only in the UK, but also globally. So the question that naturally rises is, okay, can we use hydrogen or ammonia or their mix to decarbonize these hard-to-abate industries? What these heavy-duty applications have in common is that they are predominantly powered by compression ignition engines. Replacing diesel or heavy fuel oil with ammonia or hydrogen in these engines is not really a straightforward task. There are several technical challenges to be addressed. Both hydrogen and ammonia exhibit many unique features and properties, and one common in both of them is that their high autoignition temperature, which poses a significant challenge when using them in compression ignition engines. Their autoignition temperature is simply so high that these fuels cannot burn in a conventional compression ignition engine. Now, 3 strategies have been proposed so far to tackle this. The first is to use very high compression ratios, above 30, say. Now, compared to the range of 13 to 22 roughly that conventional engines currently operate, this basically means engine redesign, which is not really cost effective. The second approach is to use a glow plug to preheat the in-cylinder air or charge. This is not in principle a bad idea, but the preheating creates several implications. Probably the most important one is that it leads to the decrease of the engine performance and to high NOx. And in certain cases, especially when the only fuel is hydrogen, glow plugs have also been reported to lead to abnormal combustion. The last approach is to use a small quantity of a second fuel, what is called a pilot fuel, which is more reactive than hydrogen and ammonia and has appropriate autoignition temperature in order to initiate the ignition. There are many benefits with this approach. One is the flexibility in operation, increased efficiency, and others, but so far, only carbon-based fuels, in fact, most of the times diesel, had been proposed for use. Now, one non-carbon-based fuel that could act as a pilot fuel or an ignition promoter is hydrogen peroxide. Hydrogen peroxide is a liquid at normal temperature and pressure, and its molecule contains no carbon at all. Recent research has also showed that it can be produced from renewable sources. Now, in my view, where it beats other green ignition promoters, say, for example, ozone, is the fact that it is already widely manufactured, distributed, and stored with diverse applications ranging from medical use to processing and bleaching certain foods, and as a domestic cleaner and disinfectant. Now, the idea of using peroxide in combustion is not actually new, and it dates back to the 1940s, when it was first used as a rocket propellant and fuel for submarines. Since then, it has been continuously used in military and aerospace applications. However, hydrogen peroxide comes with its own challenges. It is corrosive, like ammonia, and special care must be taken when its concentration becomes significantly high, that is above roughly 40%. Despite its long use in aerospace and military applications, there is very limited literature on its use in conventional combustion engines. Until recently, there was no literature on its use with hydrogen and ammonia. Now, our research aims at filling exactly that gap. For the purpose of the current seminar, I have organized the presentation of the main findings in 3 sections, starting from some fundamental aspects where we will examine 0D batch reactor ignition phenomena and 1D laminar flames. We will then move on to the theoretical examination using a simplified CCI engine model, and we will close the discussion with a comprehensive stochastic reactor engine model. Nearly all the results reported herein have already been published in a series of papers, briefly listed in the current slide, which will also be provided at the end of the seminar. Starting now with the fundamentals, here in the first part, 0D batch reactor simulations were undertaken under homogeneous and adiabatic conditions with detailed chemistry. The widely validated Aramco 3 reaction mechanism was selected for the description of the hydrogen combustion. Now, the main focus was to analyze the key chemical pathways and the dominant chemical dynamics related to the ignition delay time as a result of the addition of peroxide and steam into hydrogen and air mixtures. The conclusions were then extended to a range of initial temperatures with the purpose of identifying trends in the changes of the pertinent key chemistry. In order to accomplish the goal of identifying the key chemical pathways, mathematical tools from the computational singular perturbation method were used, as CSP is one of the most rigorous methods for analyzing highly complex multi-scale systems of reacting flows and has been successfully tested in a wide range of applications. Now, since CSP was also used in the next study, the laminar flames, allow me to present very, very briefly the method and the employed tools. Now, based on the CSP approach, the system of the species and energy equations can be cast into a new form by means of the CSP basis vectors A and B of the modes, along with the related amplitudes H. And now, when this system exhibits M time scales of dissipative nature and much faster than the rest, then the reduced model, the reduced system can be produced. Now, the equation on the left defines the manifold on which the solution evolves, while the equation on the right governs the slow evolution of the system on this manifold, and its dynamics is characterized by the fastest of the slow time scale. That is the characteristic, as we say, 1. Obviously, the identification of the characteristic time scale can be achieved in the context of a reduced model, where the fast and slow modes can be well defined. Since we will be talking a lot about modes, a mode is a mathematical quantity with no physical meaning, which is described by 2 components: a time scale, which sets the time frame of action of that mode, and an amplitude, which signifies the impact of that mode to the system's slow evolution. The physical insight is obtained when investigating the processes that compose the amplitudes and the time scales of the modes, and particularly of the characteristic one. Regarding the algorithmic tools, the timescale participation index measures the contribution of each process to the timescale of each mode. Now, when TPI is positive, it means that the respective reaction tends to promote the explosive character of that mode, while when negative, it means that the respective reaction tends to promote the dissipative character of that mode. The amplitude participation index, the API, measures the contribution of each process, that being a reaction or a transport-related process, to the amplitude of each mode. When the API is positive, it means that the respective process tends to increase the impact of that mode, while when the opposite stands when that is negative. Of all modes, we are usually interested in the characteristic one, which can be explosive or dissipative. That one must have not only a time scale among the fastest of the slow ones, but also a dominant amplitude. Now, in homogeneous adiabatic systems, the characteristic mode is usually of explosive nature, but in other systems, say turbulent flames, for example, this is not always the case, and there is literature indicating that an explosive mode can actually have negligible impact. So, special care must be taken when examining the characteristic mode and the processes associated mostly with it. Now, in both studies, though, reported here, the characteristic mode was always found to be the explosive one, the fast explosive one. Now, by combining the API values of all chemical processes for the explosive mode, the contribution of chemistry to the amplitude of the characteristic mode can be assessed, and in a similar manner, the total contributions of transport, diffusion, and convection to the amplitude of the characteristic mode can also be quantified. Starting now with the zero-D batch reactor simulations, the figure on the top left here shows that with addition of 5 to 10% of peroxide, the ignition delay time drops to roughly between 1 and 2 milliseconds. In fact, the decrease in the ignition delay time increases linearly to the peroxide addition roughly by a factor of 5, regardless the mixture's initial temperature. However, such huge acceleration of the ignition delay time is not accompanied by an increase in the equilibrium temperature. From a chemical dynamics perspective, the quantity that is correlated with the system's ignition delay time is the system's characteristic time scale, which for the cases under current study, as already explained, this is the fast explosive time scale displayed in the figure on the bottom left. This can be considered as a measure of the system's reactivity. Thus, the faster the characteristic time scale, the more reactive the system becomes. Now, it can be seen that with the addition of peroxide, the fast explosive timescale becomes generally faster. In order now to understand the change in the physics that drives the ignition process due to the addition of peroxide, the largest TPI values are presented. For the largest part of the ignition process, reaction 9F remains important, favoring the explosive character of the characteristic timescale, and its influence increases with the addition of peroxide. The increased role of 9F is reasonable, since 9F is a chain branching reaction that relates to the dissociation of peroxide to two OH radicals. In addition, the contribution of reaction 3F increases significantly with the addition of peroxide. Finally, reaction 5F, a chain branching reaction which is very well documented in the literature, becomes the most important reaction, and its influence becomes more pronounced with the addition of peroxide. Let us now see how steam affects the ignition process and the dominant chemical pathways. Starting with the effect on the ignition delay time, the figure on the top left corner shows that the addition of steam has moderate effect on the system's ignition delay time, but in any case leads to its increase. This effect becomes more pronounced as the system's initial temperature increases. The ignition delay time increase induced by the addition of steam is accompanied by a significant decrease of the system's equilibrium temperature, which is again reasonable and expected. Let us now observe on the top right panel here the time history of few species and temperature for selected cases of steam addition. Firstly, it is verified that the system's equilibrium temperature decreases, as you can see here, with the addition of steam. Interestingly, the addition of steam at sufficiently high initial quantities results in the formation of a clear two-stage ignition process. The OH and HO2 radicals increase faster with the addition of steam. However, at the end of the ignition process, their increase is not only halted, but can in fact exhibit a decrease. Let us now have a look at the CSP diagnostics, particularly at the last part of the ignition process, where the system exhibits a second ignition stage. In the zero steam case, the largest contributors to the fast explosive timescale are reactions 5F and 21F, the former favoring and the latter opposing its explosive character. The relative contributions of these two reactions are diminished significantly as the steam addition increases. Now, it is reminded that reaction 21F is a highly exothermic reaction and the main contributor to the temperature increase in the last and late ignition stage. At the same time, the contribution of reaction 18F increases, opposing the explosive character of the characteristic timescale. All these findings suggest that the second ignition stage is due to primarily the boosted role of 18F and the decreased role of 21F, and secondarily, the decreased contribution of 5F. Now, this two-stage ignition is a truly unique phenomenon, as it seems to be related to hydrogen chemistry solely. And in a sense, it seems to disprove the decades-old common belief that hydrogen chemistry can only lead to a single-stage ignition. Now, since there is no experimental validation of that yet, in fact, this is currently work in progress with KAUST, one could argue that this is an artifact, the outcome of some imperfect hydrogen chemistry modeling. This could be true, indeed, but the chances are very slim. And the reason for this is because this phenomenon appears in many different chemical mechanisms. In the current slide, the ignition delay time results from 4 chemical mechanisms are shown, and they all exhibit two-stage ignition. Admittedly, though, there are significant differences among the mechanisms on the conditions and on the conditions that the two-stage ignition exists, as this is also manifested in the ignition delay time results in all the ignition delay time results displayed in the current slide. The second important point that I would like to make is that this two-stage ignition can occur in a very distinct manner. As you can see in the heat release rate results presented on the bottom panel, the heat release rate can exhibit two peaks clearly separated from each other and with a similar intensity. In any case, experimental validation is required to affirm the existence of this unique phenomenon. Summarizing, the decrease of the ignition delay time increases linearly with the addition of peroxide. The system's fast explosive timescale becomes faster with the addition of peroxide from the beginning of the process. The system's increased ignitability through the addition of peroxide is attributed to the enhanced effect of reactions 3F and 5F, as well as 9F. The addition of steam has moderate effect on the system's ignition delay time, favoring its increase. At conditions of sufficient steam dilution, the system exhibits a clear two-stage ignition, which is the result primarily of the increased role of reaction 18F and the decreased role of 21F, and secondarily of the decreased role of reaction 5F. Now, the laminar flame study was a continuation of the autoignition work and aimed at investigating the effect of peroxide addition on the flame structure and laminar flame speed in the context of one-dimensional freely propagating premixed laminar flames. Algorithmic tools from the CSP approach were again employed to identify the key chemical pathways as well as their interaction with transport processes important to the system's dynamics. The simulations and the subsequent analysis were mainly performed at fuel-in atmospheric conditions, but the discussion with additional findings were extended to a higher temperature and pressure. Now, the figure on the top left here shows that the addition of peroxide induces a significant increase to the laminar flame speed. The strong effect of peroxide addition on the laminar flame speed is also confirmed at the high temperature and high pressure temperature conditions. At all three sets of conditions, the laminar flame speed change is roughly linear to the peroxide addition. Now, the two figures on the top right display the H-chem and H-diff, that is, the summative contributions of chemistry and diffusion, respectively, to the amplitude of the system's dominant mode in the absence of any peroxide in the mixture, along with the explosive timescale and the heat release rate. It is shown that the contribution of diffusion becomes greater for temperature less than 670 Kelvin, and that region can be described as the preheat zone, while the contribution of chemistry becomes greater for temperatures between 670 and 1150 Kelvin, and that region can be described as the reaction zone. Also, a comparison of H-chem with the heat release rate reveals that they are very well correlated in the progress variable space, corroborating further the use of H-chem as an indicator of the reaction zone. Now, the figure on the bottom left shows that the addition of peroxide makes the fast explosive timescale to become faster and the respective amplitude to become larger, suggesting thereby that the system's dominant mode becomes more active and its impact increases. Notice also that the explosive timescale exists for higher progress variable values, thus extending the region in the progress variable space that affects the system's dynamics. Finally, the two figures on the bottom right show that the addition of peroxide increases the region in the progress variable space where chemistry has a larger relative effect compared to diffusion. In other words, the reaction zone increases while the preheat zone decreases with the addition of peroxide. this effect becomes more pronounced at higher pressure and temperature conditions. In order to appreciate in more detail the changes in the flame structure and identify the processes that are responsible for the reaction zone broadening as a result of the peroxide addition, the largest API values are displayed for two separate pressure and temperature cases. At atmospheric conditions, the addition of peroxide affects the flame structure by enhancing the effect of the chain carrying reaction 10F, which in turn enhances the influence of 3F. The pathway of 10F and 3F is the main reason for the radical pull enhancement and the broadening of the reaction zone. At sufficiently high temperature and pressure conditions, the addition of peroxide affects the flame structure primarily through reaction 9F, which in turn causes a notable increase to the relative contributions of reactions 3F, 5F, and 15F. The changes related to these reactions is the main reason for the broadening of the reaction zone due to the addition of peroxide at high pressures. Although chemistry plays an important role to the dynamics of the examined laminar flames, the role of diffusion should not be dismissed. The figure on the left shows that the addition of peroxide leads to the increase of the effective Lewis number, therefore favoring the thermodiffusive stability of the laminar flame. To investigate further the non-unity Lewis number effect, additional cases both at the low and high pressure conditions were simulated. The two figures on the right display the evolution of H-chem, that is the summative contribution of chemistry, in the progress variable space for the 0 and 10% peroxide addition cases at the low and high pressure conditions. On the top of these results has been overlaid the H-chem evolution for the same conditions, but now fixing the Lewis number to 1. Firstly, it is shown that when Lewis number is 1, the addition of peroxide results again in a broadening of the reaction zone. However, in that case, the reaction zone broadening becomes significantly decreased. These findings can be explained when the main mechanism that peroxide affects the flame structure is considered, that is, the increase of the radical pull either through the reaction pathways of 10F3F or through 9F3F and 15F, depending on the conditions. The larger diffusivity of the reactants compared to the thermal diffusivity becomes more effective in an enhanced radical pull, leading thereby to the broadening of the reaction zone. Summarizing, the peroxide addition leads to a substantial increase of the laminar flame speed. The reaction zone is increased with the addition of peroxide due to the increased radical pull that is achieved. Peroxide addition alters the flame structure in a way that increases the importance of the chain carrying reaction 10F or the chain branching reaction 9F, depending on the conditions, of course. The increased effect of reaction 10F enhances in turn the effect of 3F, while 9F increases the influence of reactions 3F and 15F. The changes induced in these pathways are mainly responsible for the radical pull increase and the reaction zone broadening. Finally, peroxide addition tends to make the laminar flame less thermodiffusively unstable. With that, we conclude the first section, and we now move on to the second section, which concerns a theoretical study using a simplified engine model. In this theoretical study, a 0D single-zone HCCI model has been used, which solves the species and energy equations, along with an additional equation for the volume change. The intake pressure was 1 atmosphere, and the intake temperature 320 Kelvin. Peroxide was added on the basis of the hydrogen mole fraction. I have organized the results in two parts. In the first, we only consider hydrogen and hydrogen peroxide blends, so no steam addition. I will start with a comparison against the glow plug approach, that is the preheating of the mixture, then discuss the effect of peroxide addition on the engine performance, and close with the investigation under constant and low load conditions. In the second section, steam dilution is included. Firstly, I will present a comparison against the glow plug approach, and then discuss the effect of both peroxide and steam addition on the engine performance. So let's start with the first part. The investigation was performed in a range of equivalence ratios and engine speeds. In each case of peroxide addition, it is compared against the respective glow plug approach, which means we remove the peroxide from the system, from the initial conditions, and properly increase the inlet temperature. For a fair comparison, we ensure that the ignition occurs at exactly the same degrees between the two cases. For example, at phi equal to 0.1 and 1000 RPM, we used 12% peroxide to achieve an ignition crank angle degree equal to 1.89. And in order to achieve the exact same outcome without any peroxide, we had to increase the inlet temperature to 386 Kelvin. In summary, the comparison against the glow plug approach reveals that as the mixture becomes richer, firstly, the required peroxide addition to achieve ignition at roughly 2 degrees decreases substantially. Secondly, IMEP, power, and torque all increase significantly with the addition of peroxide, but as the mixture becomes richer, their increase drops. On the other hand, peroxide addition also affects thermal efficiency and NOx, but as the mixture becomes richer, its impact remains unaffected, in that thermal efficiency only slightly increases and NOx decrease substantially. The results already discussed provide us some insight as what to expect when investigating the incremental increase of peroxide content at the initial mixture. So in terms of the ignition CAD, the addition of peroxide results initially in drastic reduction of the ignition CAD, and further addition has negligible effect on the ignition promotion. Therefore, the ignition CAD basically levels off. This profile becomes attenuated at very lean conditions, that is phi equal to 0.1, and in fact, as the engine speed increases, the dependence of ignition CAD on the peroxide becomes roughly linear. In essence, as the mixture becomes richer, and regardless the engine speed, the effect of peroxide addition on the ignition promotion becomes more pronounced. In terms of IMEP, the increase that hydrogen peroxide induces seems to be mostly linear. If we are to look at the gradients of these profiles as a measure to assess the sensitivity of IMEP to the peroxide addition, we would find out that as the mixture becomes richer, peroxide addition results in stronger impact. So basically the gradients become steeper, but the rate of this change becomes smaller. In the last part of the analysis, we gradually increase the peroxide content while also reducing the equivalence ratio in a manner that the load is maintained constant at roughly 34 Newton meters. And we did that in a range of engine speeds. This section further corroborates the strong effect of peroxide addition on the thermal efficiency. In addition, it is shown that NOx emissions are extremely low at all cases of peroxide addition and engine speeds, which is attributed to the generally low maximum temperatures. So we covered the first part of the theoretical engine investigation. Let's now add steam dilution into the system to see how this would work. In the comparison against the glow plug approach, we considered heat losses and kept fixed the peroxide content at 5%, and also added incrementally steam dilution into the system from 0 to 10%. Then we removed the peroxide and tried to reproduce the same load output by properly increasing the inlet temperature, and the result in terms of IMAP and torque is shown in the figure on the left. In most cases, increasing the inlet temperature was not sufficient, so we also properly increased the equivalence ratio additionally, and this is shown in the figure in the middle. For instance, to achieve an IMAP value of 7.4 with 6% of steam dilution, with peroxide, we achieved that by adding 5% at phi equal to 0.4, but with the glow plug approach, we had to increase the inlet temperature to 376 Kelvin and the equivalence ratio to roughly 0.54, that is a 34% increase. Now, the figure on the right compares the two approaches in view of thermal efficiency and NOx emissions, and the benefit of the use of peroxide is showcased again. In fact, as steam dilution increases, the decrease in NOx increases and reaches 2 orders of magnitude difference. Thermal efficiency is also significantly affected, and the difference between these two approaches becomes more pronounced mainly because of the increase of the fuel mass in the case where no peroxide is used. Next, we consider the effect of both peroxide addition and steam dilution on IMAP and NOx emissions. The x-axis represents the peroxide addition, and the y-axis denotes steam dilution. We are interested in the areas where NOx are low, that is red color, and IMAP is high, that is purple. Generally, both IMAP and NOx increase with the addition of peroxide and decrease with the steam dilution increase. So, for instance, at 1000 RPM, where phi is equal to 0.3, we can see basically that NOx are low for all conditions, except perhaps for peroxide higher than 15% and steam dilution less than 3%. Summarizing the findings with a simplified engine model, firstly, the proposed approach seems to be clearly advantageous against the glow plug approach and the preheating of the charge. Secondly, the addition of peroxide results in the increase of IMAP and torque while also greatly decreasing NOx. Thirdly, steam dilution could be an invaluable tool offering unique operational flexibility since it can reduce tremendously NOx emissions. That, in combination with a balancing of the equivalence ratio, can require less than 10% of peroxide regardless the operational requirements. And with that, we now move on to the last section of the study, potentially the most interesting one, where a detailed and sophisticated engine model was used. So far, all the investigation concerned hydrogen as main fuel. In this last section, mixtures of ammonia and hydrogen were considered. A stochastic reactor engine model was employed, available in the SRM engine suite. I'm not going to describe in detail the model, as I would like to focus more on the results, but I will say that the numerical model solves a joint scalar PDF transport equation using a stochastic numerical method, and that it accounts for processes associated with the chemical source term, turbulent mixing, piston movement, convective heat transfer, as well as fuel injection. The results are organized in two parts. In part A, the initial in-cylinder pressure and temperature were set to 13 bar and 390 Kelvin, representing thereby mild boost and efficient intercooling, while also avoiding the condensation of water vapor. The ammonia concentration in the ammonia-hydrogen blend was maintained constant at 80% per fuel mole fraction for all simulations, except for the cases that the hydrogen share was the variable being tested. Injection parameters were adjusted with the understanding that the injected peroxide solution should occupy less than 10% of the volume of the ammonia in the combustion chamber when in the liquid phase. The motivation for this approach is that in a dual fuel system, it is desired to minimize the dependence on the second fuel and hence limit as much as possible the size of the respective fuel tank. In energy terms, the injected peroxide solution was less than 0.1% of the main ammonia hydrogen mix used. In part B, the initial intake mixture temperature was decreased by 60 Kelvin to 330 Kelvin. Peroxide was assumed to always be diluted in water in concentrations equal to 30%, unlike part A, where the peroxide concentration was at 10%. Also, in part B, multiple engine speeds were studied. In both parts, the simulations were initialized with a mixture of ammonia and hydrogen at an equivalence ratio of around 0.5. Let us now start with part A, and particularly the hydrogen share analysis, where the initial concentration of hydrogen in the ammonia-hydrogen blend was varied from 10 to 40%. In the two figures on the left, we can observe that by keeping the mass of the directly injected peroxide solution fixed at 4 milligrams, no combustion occurs when hydrogen is 10%, while when this is increased to 20%, the mixture combusts, but the combustion occurs late during the expansion stroke, and increasing further the hydrogen share leads to strong combustion. Looking now at the effect of hydrogen share on various key engine quantities for different injected peroxide masses, we can observe that the amount of peroxide pilot fuel has little effect on torque, thermal efficiency, combustion phasing, NOx emissions, as well as pressure-related variables. We can also observe that peroxide solutions so low as 1 milligram can successfully ignite ammonia hydrogen shares with hydrogen shares between 20 and 25% with acceptable pressure rise rates. At these optimal hydrogen share conditions, CAD 50 varies between 10 and 20 CAD, and the main combustion duration varies between 11 and 24 CAD, depending on the directly injected masses. Although not explicitly shown in these figures, the results presented here demonstrate that the direct injection of 1 milligram of peroxide solution in combination with 20 to 25% hydrogen share suffices to achieve more than 60% load of the engine's rated power. The only downside is that at the optimal conditions of 20 to 25% hydrogen share, NOx emissions remain above IMO's Tier 3 limit, roughly 1 order of magnitude higher. In the next step, the aim of the analysis was to investigate the effect of the amount of the directly injected mass at different injection degrees. The strong effect of the direct injection of the peroxide solution is firstly displayed in the two figures on the left, where it is shown that 1 milligram suffices to enable the ignition of the charge. However, the ignition in that case occurs quite late and the combustion process is very, very slow. This phenomenon is due to the fact that peroxide and water act competitively in the combustion process. On one hand, peroxide tends to promote ignition by enhancing radical regeneration, while water tends to reduce combustion temperature. When the injected mass is sufficiently low, misfire occurs as the ignition promoting character of peroxide is weaker than the effect of water. With the increase of the directly injected fuel to 4 milligrams, the ignition process is significantly accelerated. The effect of the mass of the directly injected peroxide solution was further investigated in a more systematic manner in view of the indicated torque and the combustion duration, the pressure rise rate, and specific NOx emissions. From the results presented in the figures on the right panel, we can conclude that 4 milligrams of directly injected mass of peroxide solution suffices to achieve a torque of roughly 620 Newton meters, which is 65% of the rated load. Any further increase of the directly injected mass has negligible effect on the developed torque. The increase of the directly injected mass of the peroxide solution has a notable effect in decreasing the combustion duration, although this increase diminishes as the directly injected mass increases. In all examined cases, the maximum pressurized rate was always well below 50 bar per millisecond, which can be considered the threshold for safe engine operation. Finally, specific NOx emissions appear to increase with the directly injected mass and with advance of the start of injection. For directly injected masses between 2 and 4 milligrams, specific NOx were again an order of magnitude higher than the values regulated by IMO Tier 3 standard. The scope of the next part of the analysis is to explore the changes in the engine performance as a function of the load. The variation of the load is achieved by adjusting the initial mass of the ammonia-hydrogen mixture. Any change in that mass directly affects the in-cylinder global equivalence ratio. As a result, the equivalence ratio changes from 0.32 to 1.2 by adjusting the mass of the ammonia-hydrogen mixture from 65 to roughly 200 milligrams respectively. Apart from the mass of the ammonia-hydrogen mixture, all other parameters are maintained constant except for the mass of the directly injected peroxide solution, where 3 cases were considered: 4, 8, and 16 milligrams. Firstly, we can observe that load variation between 44 and 93% can occur. Load enhancement is almost perfectly linear with the increase in the equivalence ratio peaking at phi equal to 1. The combustion duration is affected more by the directly injected mass than the equivalence ratio of the initial mixture. The maximum pressure rise rate is a function of both the directly injected mass and the equivalence ratio of the initial ammonia-hydrogen mixture, increasing with the increase of any of these two. In all cases, the maximum pressurized rate is maintained below the threshold of 50 bar per millisecond. NOx emissions peak between phi of 0.6 and 0.65 and rapidly decrease as the equivalence ratio increases or decreases. At high load conditions, NOx emissions are marginally above the Tier 3 standard. Ammonia slip is negligible for any of the investigated conditions, with the only possible exception at low loads, where the load is 44%, and highly lean conditions, where the unreacted ammonia reaches around 7% of the initial ammonia mass. Finally, N2O emissions are negligibly small for all the investigated conditions. Moving on to part B, where the initial mixture temperature decreased to 330 Kelvin and multiple engine speeds were investigated. For the purpose of the current presentation, the discussion will focus on the effect of the concentration of peroxide in the solution. I note here that the hydrogen share in the ammonia-hydrogen mixture needed to increase to 30% for the low and medium in engine speeds and to 40% for the higher engine speeds. Before we start looking at the engine simulation results obtained from different peroxide concentrations, let us first examine how the change in the peroxide concentrations alters few of the solution's key properties as summarized in this table. Firstly, the increase of the peroxide share increases the mixture's energy density, thereby enhancing the combustion process. But that energy density is generally quite poor, especially when compared with fuels like diesel. Secondly, the standard enthalpy of evaporation of peroxide is quite high, and this has an adverse effect on the combustion process as it tends to make more pronounced the cooling effect during the direct injection of the mixture. Another important finding is that although on a mass basis, 4 milligrams of directly injected peroxide solution represents roughly 5% of the ammonia hydrogen initial mass, on an energy basis, this ratio is significantly lower and ranges between 0 and 0.63%, depending on the hydrogen peroxide share in the solution. In principle, increasing the peroxide share in the directly injected solution tends to advance the combustion process, as indicated by the pressure and temperature histories in the figures on the bottom. Also, the peroxide solution is shown to enhance the radical pool generation as manifested in the time histories of OH and H radicals. Notice something interesting here though. This radical pool enhancement is not accompanied by a similar temperature increase. Let us now observe the effect of different peroxide concentrations on some engine performance characteristics. Starting with the effect of the indicated torque, the progressive increase of the peroxide share has in principle a positive effect regardless the engine speed, leading to initially a relatively rapid increase of the torque, which later seems to level off. Note that the torque developed with a peroxide share of 30% at all engine speeds is extremely close to the maximum possible. The thermal efficiency exhibits a slightly different response. This occurs because the mass flow rate is maintained constant as the peroxide share increases, but the overall fuel heating value increases linearly. Therefore, the denominator in the definition of the thermal efficiency increases linearly with the increase of the peroxide share. At the same time, the power has a weak local maximum, resulting in the response shown in this figure. The ignition advance achieved by the increase of the peroxide share is reflected in the value of CAD 50. As already argued, the main reason for the ignition advance induced by peroxide stems from its ability to enhance the radical pool. Here, this argument is corroborated further. Now, the figure on the right here displays the variation of CAD 50 as a function of the maximum molar concentration of OH. It is evident that CAD 50 advances in an almost perfectly linear manner with the maximum OH. The shortening of the combustion duration and the advance of CAD 50 because of the increase of the peroxide share is expected to result in a more intense combustion manifested by the maximum pressurized rate. This expectation is indeed confirmed as shown by the figure on the bottom left. At most examined conditions, the maximum pressurized rate does not exceed 30 bar per millisecond, but for sufficiently high peroxide shares, the maximum pressurized rate can in fact increase significantly even above the threshold of 50 bar per millisecond. These excessively high pressurized rate values are most probably due also to the increased hydrogen share in these mixtures. Let us now talk about emissions. NOx emissions progressively increase with the increase of the peroxide share at all engine speeds. However, this trend becomes less pronounced with the increase of the peroxide share and tends to level off. NOx emissions are inherently coupled with the combustion temperature. Hence, it is natural to expect some correlation between the maximum temperature and NOx emissions. The figure on the top right corner confirms a closely linear correlation in the variation of specific NOx against the maximum temperature. Similar to the results reported in Part A, the NOx values reported here exceed the IMO's Tier 3 standards by an order of magnitude. On the other hand, the ammonia slip ratio is extremely low in all examined cases, reaching a maximum of 0.7%, and it is negatively correlated with the peroxide share in the directly injected solution. Specific N2O emissions are similarly negatively correlated with the peroxide share in the directly injected mixture. However, this correlation attenuates with the increase of the peroxide share and appears to level off at sufficiently high peroxide share values. A major reason for these relatively high N2O emissions is the low combustion temperature, and in fact, the maximum temperature for most of the examined cases never exceeded 1750 Kelvin. Summarizing, the required amount of aqueous hydrogen peroxide could be as low as 0.09% on an energy basis or 2.5% on a volume basis of the ammonia hydrogen mixture at medium and high loads. Secondly, the analysis highlighted that the concentration of the peroxide in the solution can be as low as 10%. The introduction of peroxide was found to strongly favor the enhancement of the radical pool generation, although there was no effect on reactant temperature by the end of injection. The analysis also revealed that generally no excessive pressurized rate arise that would prohibit the use of the proposed technology. The proposed technology nevertheless results in NOx emissions, which in many of the explored conditions exceeded the Tier 3 standard, thereby necessitating potentially the need for some after-treatment. Ammonia slip was generally found to be negligibly small. Finally, N2O emissions varied significantly, but there were many conditions where they were found to be extremely low. Load variation between 44 and 93% was achieved by adjusting the equivalence ratio of the initial mixture. This study presents some very promising preliminary results. It provides grounds for further investigation into the full scope and limitations of this technology, which necessitates conducting extensive engine experiments as well as advanced high-fidelity numerical simulations. The work also highlights the necessity for more extensive analysis of the optimal configuration to achieve balance between engine performance and specific NOx levels. There is a need for more detailed examination of efficient design parameters for engine operation utilizing this technology. And with that, I would like to thank our funders so far, and I will happily take any questions now.
Okay, thank you very much. Thank you very much for this interesting talk. Stathis, we open now. Professor Parente is doing exams, and now he had an exam started 5 minutes ago. So I will replace him in sharing this Q&A. So I will ask the audience if there are any questions that you want to ask. Please feel free to ask. Just raise your hand or unmute yourself and feel free to ask. Okay. Since there are no questions so far by the audience, from the audience, so I will start. I will start from your concluding remarks that talk about all the questions that came up to me. One would be regarding the experiments, and so the feasibility of actually injecting a corrosive agent like hydrogen peroxide along with a reactive substance, reactive like hydrogen. And so, yeah, what do you think about the feasibility of these experiments, also for practical applications of this type of engines in the near future?
Sure. One thing is the corrosiveness, and the other is the safety aspect. Regarding the safety aspect, this can be addressed if the concentration of peroxide in the solution is sufficiently low. So, that's what we have been exploring in our studies so far. So, our aim has been to use a peroxide that can be easily found in the market. So, which has concentration up to 30%, I believe. So up to 30%, you can find it pretty much quite easily in the market. So there is the safety aspect is not really an issue. If you exceed that, then safety, yeah, it could become an issue. For the corrosiveness, well, I would argue that ammonia is also corrosive, but still we're discussing this as a main fuel. So there must be definitely some consideration with regard to the corrosiveness, but I don't think that would be that would pose a significant barrier for the development for the further development of this technology, or for any experiments really. I believe by keeping the concentration of the peroxide in the solution low, relatively low, it wouldn't pose any significant issue. And besides, just to mention also that peroxide has been used in experiments, in engine experiments in the past, but it hasn't been used with ammonia and hydrogen. There is some literature, there are very, very few studies really, but it's not that it hasn't been used at all.
Okay, so there's already some sort of technological readiness to inject peroxide in engines.
I would say it's pretty low. It's quite low still, but and again, the literature is scarce, but it's not that it hasn't been done at all. The part that hasn't been done is the combining peroxide with ammonia and hydrogen in order to develop a fully carbon-free technology. That's what our research aims to, the gap that our research aims to fill in.
Okay. Well, I remind the audience that they can interrupt us any moment if there are any questions, because I have another questions regarding like you said, the need for validation experiments, and also my question is related more on the uncertainty of the models that you have used. So meaning about the engine model, and also the chemical reaction mechanism that also showed there might be some important uncertainties. So yeah, my question would be how uncertain are the results you have shown, and so how important is to have indeed experiments to validate and somehow reduce these uncertainties.
Sure. Yeah, it's a reasonable and hard to fully address question, I admit, because as I said, since there are no experiments with this technology, I mean, one could argue that, how much confident are you? Well, for the engine experiments, what we did, we used an engine model that was previously validated, but with different fuels, not obviously with ammonia, hydrogen. So we used a validated model with different fuels, and in that we replaced hydrogen. We use hydrogen and ammonia as main fuels. So yeah, I'm not in a position to quantify the confidence or the uncertainty here, but I would say that there is some reasonable confidence on the results, since the engine model was validated, to some degree. Now, with regard to the mechanism, that's also an interesting question, because especially when it comes to the two-stage ignition that we have reported, as I explained, I mean, if you look at the mechanisms, if you look at different mechanisms, you will get different results. Quantitatively, yes, you will get different results. But qualitatively, especially when it comes to the two-stage ignition, I have tested multiple mechanisms, not only those that I showed, and all of them exhibit this two-stage ignition. So I haven't actually found any mechanism that doesn't exhibit this unique phenomenon. So I would say that I would say that I'm very confident that the results qualitatively are correct. There may be some uncertainty on quantitatively, but again, this can only be addressed by experiments.
Okay.
So if I
thank you. Yeah, please go ahead.
Thank you. Thank you, Stathis, for the great presentation. It's good to see you again. So if I can just follow up on this question, in your expertise, like which parameters might be interesting if we want to conduct like an uncertainty quantification analysis? Would the focus be more on the physical parameters or on the parameters within the chemical models?
Thank you, Marie. Nice to see you. So yeah, I believe the problem is with the chemical models. So I would focus on the parameters, on the specific parameters, and particularly I would particularly focus on specific reactions, and I have few ideas on which these reactions should be, and yes, what you suggest makes perfect sense. So, and the uncertainty analysis would be ideal for that purpose. So yeah, I'm happy to take this further with you if you're interested.
Yes, absolutely. Thanks.
Thank you. We have a question in the chat from Charles Louis. Sorry if I mispronounce your surname. He's asking, what is the status of planned and ongoing experimental studies on hydrogen peroxide and hydrogen ammonia mixtures?
So, there is some. So generally, this is dependent on the funding. So currently, we are quite tight with the funding situation with our collaborators at Imperial College, but we are trying to. We are doing our best to have some engine experiments working very, very soon.
Okay, thanks a lot. I guess we can close here the Q&A section, and I would like to thank you again, Stathis, for your talk and for your availability to discuss these further points, and hopefully you can find your fundings, you and your group, your collaborators can find funding to really address these issues to further improve and assess these interesting results that you have shown us today. So thank you,
Salvatore.
Again.
Thank you for the invitation. Thank you all.
Thank you all for attending this webinar, and I'll see you all at the next appointment. Have a nice weekend, everyone.